Hello everyone, thank you for joining us today for this final internship talk by Shivam, Mehta. Shivam is a PhD student at KTH in Stockholm in Sweden, and where he works on speech processing and probabilistic generative modeling. And today he'll talk about llamas, right? So with that, Shivam, take it away.
Perfect. Hello everyone, welcome to my talk. My talk style makes some noise, teaching the language of audio to an LLM using sound tokens. I'll give the motivation behind this entire project. It was like foundation models, they undergo pre-training on large data set, which result in these emergent abilities and like how good they are in conversation and assistant. Everyone is aware of using them right now. And can we extend, so the question was, can we extend these abilities to the language of audio? What I call language of audio right now is like more discrete tokenization, which I will talk about later. And can we leverage these LLMs and can train them in a next token prediction task in a very common way? The LLMs are trained, but you just give them a bunch of training data in an unsupervised setting, and you're like, here, learn to predict the conditional distribution to generate the next token, given the current and the previous token. So my talk is basically divided into 5 parts. I'll give a bit of background, starting from back in old days, and then LLMs and tokenization, LoRA, multimodal LLMs, and LTU and seed from the fusion of these two models, which we tried to make. Talk more about our approach, which we also break it down into 2 steps. One will be audio tokenization, and the other will be fine-tuning a language model. And then I'll get into more details about the tokenization of audio and the LLM. And finally, there will be some results and conclusion. Hopefully, yeah, I'll do justice to them, or they do justice to me. So background, it all started with the GPT as a language model. When everyone, when transformer encoder decoder came out, everyone started this it revolutionized neural machine translation. And then a couple of researchers from OpenAI back then, they were like, what if people from Google, they made BERT, where they were like, what if we take the encoder part of the encoder decoder model and get something out of it? And then OpenAI came up with the GPT, where they just took the decoder part of it, which is a causal language model, and saw that, oh, can we train that as a language model? So they proposed to use this decoder-only network, only transformer for language modeling. And then in the next version of GPT, they introduced this line. They said that when a large language model is trained on a sufficiently large and diverse data set, it is able to perform well on many domains and data sets. And this is where the hell went loose. And then all it was, now came the era of large language models. You feed in more compute, more data. Models start to get bigger. They start to get better with results. And but one of the important aspects of having this next token prediction is the part token. So I'll talk a bit about tokenization. Since our work is based on Llama, I'll emphasize more on the Llama's aspect. Llama uses this tokenization, which it's a sentence tree tokenization. It takes the text and chunks down into into tiny atoms, which are most frequent to this vocabulary. And the tokenization is sort of color coded, and this is how a token becomes for the next token prediction. Yeah, so basically for models to process text, it needs numbers. It needs to be represented with numbers. And tokenization also serves as a way of limiting the size of the vocabulary that the model needs to learn while discretizing the next text into tokens. So for Llama-based, Llama 2 that we used, the tokenization, the vocabulary length was 32,000. And once you have these tokens, you can learn to predict the next token given the previous token. What I mean is like, oh, you have a start token, and then you're like, oh, this, and now I have a start, and this token will be the next token is. And then the start, this is an example. Oh, okay, so basically this is how you learn the tokenization of it. But then language models were large, and which basically means a lot of flops you needed to backpropagate through them. Forward pass takes 2 into n petaflops, and then backward pass 4 times the number of parameters. So that's a large compute. Not everyone had this, So Microsoft actually came up with LoRA, which is called low rank adaptation. The idea behind this is that, basically because LLMs are massive with billions of parameters. So the idea was, what if we break down a weight matrix into two small low rank matrices, and then we take the outer product of it, we train only that, and then fuse it to the original weight, and boom, you have a updated weight. So you don't need to backpropagate through the entire, only forward pass through this. So you save a bunch of flops there, and you only train these two A and B matrices, and you get new parameters out there. And you can put this in every linear layer, which we also did. So all the attention layers, query key values, and feed forward layers, you can put it in there. And once, and with the help of this, one can fine tune any pre-trained model on their dataset, or on any whatever they want. Like I have a specialized dataset that I want the model to learn, so I can basically put this in, and can even train it in lower precisions for like as low as like 24 gigabytes of memory for a Llama model, which is pretty cool when you think about it. And now I will introduce a bunch of multimodal approaches. So these LLMs have jumped out of just text as a modality. People have tried to use these abilities or these large information on different modalities as well. First, multimodal understanding. There has been Llama, perceivers, etc. for vision, and for audio. This is the main one that I'll be focusing on and comparing against. Is called listen, think, understand. Which, but the common thing between these two modalities, or between these two architectures, is that they treat all the other multimodal modality as some continuous input, which sort of restricts them to do the next token prediction. So the input is multimodal, but the output is still text. They never learn to generate anything except for text. Then Seed Llama came up with a multimodal generation idea. They were like, what if we quantize these image representation? And they introduced the idea of having a causal left to right Q-former quantization, so that the current token only has access to the previous one, which is also how LLMs sort of learn. So they introduced this bias inside while learning the code book, and they proposed this quantization. And then once they have this quantization, they said, now we can teach the model again to do a next token prediction task. And they train a multimodal language model which generate these image tokens, and then they use unclipped stable diffusion to go back to image domain from once they have these tokens. So now we have some idea of like, we can feed in stuff and have a bit of understanding ability. And if we somehow discretize it and train it long enough with long data, perhaps we might get multimodal generation. By the way, they trained for 32 days on massive nodes and clusters to get these image generation capabilities. So our approach, we were inspired by the Seed's causal image tokenizer. And we were like, we want to make Llama hear and make noises with audio tokenizer. I also want to showcase my great prompting skills when generating image from Copilot. We and Hen especially like the third one. So we broke the problem into two steps, where we were like, first we try to tokenize the audio, get these tokens out, and then we will train a multimodal language model with sort of, again, early fusion idea of text and token, put them as a language of tokens, and then try to train an LLM out of it. Spoiler alert, this is hard. But yeah, so I'll talk about audio tokenization. One of the problems when working with audio is that audio waveform is a lot of data. When we restricted, we were like, okay, we will try to generate 10 seconds of audio waveform. Our audio was sampled at 44.1 kilohertz, and then we're like, that's a lot of data points to generate. And there's no way with the quadratic complexity of a transformer model we can generate this much waveform in a feasible manner. So good thing, just 3 days after I joined, Stable Audio came up with a Stable Audio Open 1.1. Stability came up with a Stable Audio Open 1.0, which had a VA that operated at a much lower bit rate than the waveforms. And so the idea was like it could downsample 10-second audio into 215 and 64 continuous vectors. So now you have 215 temporal dimension and 64 spatial dimension for a 10-second of audio, which before was 40,000-ish data points. But to generate, again, we were looking of quantizing things, and like we need tokens to run the next token prediction loss function. So we need the cross entropy to be minimized over the set of tokens. First, I'll show some of the reconstruction of this. It reconstructed very well for the amount of bit rate it's operating on. Music. Wait. Again, we need tokens, but yes. And this is the reconstruction. Speech.
Many animals of even complex structure which live parasitically within others are wholly devoid of an alimentary cavity. Many animals of even complex structure which live parasitically within others are wholly devoid of an alimentary cavity.
General audio. And the reconstruction is also pretty good for this. But there were also some failures where it could not reconstruct when it was just a lot of noise. This is the original, and now the reconstruction. But it was good enough to start with. So we get all our data, we ran it through the VAE, and we got a more compressed representation. We're like, if we reconstruct this, we get almost the reconstruction that we need. Almost being the word. So we thought of vector quantization and taking this idea from seed Llama paper that what if we also have this causal attention mask, we might get this language, like tokenized language sort of stuff. So we freeze these VAE encoder and decoder and generate continuous latent for the audio, represented as code here. And we pass this continuous latent vector to a causal transformer. We quantized using normal VQ-VAE based VQ operation, and then use the transformer encoder block to reconstruct. This was non-causal, and this just basically tries to reconstruct this, and then train it with a mean square error between the reconstruction and the latent. And then we trained it for a while, and these are the data sets that we used. We chopped all the audio samples in 10-second files from the following data sets. It was quite a lot of data. It worked pretty good. So I will. But now, when you think about the bit rate, became ultra low, because now you have for 44, let's say 1 second audio, for 1 second of audio where you have 44,000 data points, now you are transmitting the same information with 21.5 integers from an 8,196 codebook. So I'll show some reconstruction of this.
Many animals of even complex structure which live parasitically within others are wholly devoid of an alimentary cavity.
Many animals of even complex structure which live parasitically within others are wholly devoid of an alimentary cavity.
We can obviously hear some artifacts.
What is the size of the codebook?
8,000. So it's quite compressed representation for audio, general purpose audio also. But then we were like, when you train a VQVAE, there's often that in many literature you will see that people add like a discriminator loss so that the VAE becomes a bit more of a mode-seeking behavior, because it's easier to sample something near the data set than to come up with something new. So you can bias the VAE generation a bit towards what you already have in the data set and stuff. But GANs are tricky to train, and I couldn't train a bigger network due to some training instabilities. But then we were like, there's more recent version of strong generative models, probabilistic in the sense, which is called conditional flow matching. So we were like, what if we put a diffusion transformer as a decoding backbone and train a conditional flow matching process to reconstruct these latents? And we trained it. It turns out it works actually pretty good. And being a good generative model, we could generate things with at least bit better quality. So again, I'll play the original again, perhaps stop in the middle.
Many animals of even complex structure which
Many animals with even complex structure which live parasitically with their others are wholly devoid of an elementary cavity.
Chicken speech is easier to model than human speech. Oh yeah, perhaps I don't speak chicken. Yeah. So basically, then we also compared these two approaches, the one with the reconstruction with the mean square error and the reconstruction with flow matching. We used 100 samples from 3 data sets, and the model was not trained on the data sets in itself. So the entire data set was out of distribution for what model was trained on. And we saw that vector quantization with flow matching, actually, even though the mean square error one was trained to minimize the mean square error, but the model had, a stronger probabilistic model had more flexibility to generate things more closer to what the data was, especially when the data is out of distribution. So that then the average was not the good approximation. Then learning a distribution is a better idea. This is very evident, especially in FMA, where you have, which is like a music data set. And our hypothesis is that the stable audio, since it's also trained on a lot of music data, has a bit more bias in the representation about music. But yeah, lower, this is the reconstruction error, so the lower the score, the better it is. We also computed Fisheye audio distance for these two approaches. And then we saw that with CLAP, we used the VQ with the flow matching gain lower audio distance than the one with the mean square error. And we also did speech quality estimation, even though the speech is pretty terrible in reconstruction. But we still tried to do a speech quality estimation. And then we saw, even though terrible, still the flow matching one was better than the mean square error one. And I think we could also hear that today. So, but yes, now we have tokens. So basically this was a success that we have tokens, and we're like, that are learned in a left to right manner, just like language. Perhaps now we can use them to train an LLM. And so we did. So I'll talk about stages of LLM training. Everyone talks about LLM. You have a pre-training stage, then you have a fine-tuning or instruction tuning stage. You also can have like more RLHF and more safeguarding stages, but we stuck with these two given the timeline we had. In the stage 1 for pre-training, we used so Listen, Think, Understand paper also introduced a data set called OpenAQA, which had the 3 sets. One of them is a closed caption set. So in that you have an audio and you have a caption for that. So for pre-training stage, we only trained the data with the closed captioning. So we put, so the audio was essentially put something like and we swapped the location of audio and text randomly. So you would have sometimes audio in the beginning, and then you would have the caption, or you would also have the caption in the beginning and you would have audio. So the idea was for pre-training that the model just needs to learn the next token prediction. It doesn't follow the instruction, we don't care. The idea is like, this is how the languages reduce the entropy, reduce the perplexity of this to learn. And then, but now we had a base model that could be used for like an autocomplete task. So if I give it an audio and like give it the initial prompt like audio caption or this audio has, and press enter and let it generate autocomplete my audio, it will actually start doing decent job. So it was the audio, and I'm like, okay, I wrote audio caption, colon, and then I was like enter. And then it says, a drum loop is playing, which is, okay, good caption, valid caption. So the idea is you input the audio, tokenize it, and let it caption it for you with an autocomplete task. Then again, one other example is that I put an audio, and the audio was this. And it says a guitar is playing a song. And again, it will not be very chitty chatty. It will not talk to you. It will not describe. Its job is just to caption what was given, and it captions. But unfortunately, with the given data, given training time, and the given data we had, it didn't learn to generate, it didn't learn to generate meaningful things. It would generate series of audio tokens, or repetitions of series of audio tokens, but we could not render them into meaningful audio. Sometimes it will work, sometimes it will not. Like, you would see that it is trying to get there, but it's severely undertrained. So some examples for generation is like, I gave it the input was like the audio described the sound of a police car with siren. That's all, yeah. Okay, and then, it was a big improvement after listening hours of noise. So, which follows now, like the audio describes guitar playing in the background, and that's all. So yeah, it didn't learn. So the siren was actually surprisingly good. I was not expecting that. Okay. So then we were like, okay, in the interest of time, we had to move on to the next stage. So we put whatever data we had the 6 million data. So before the data set was 2 million audio samples, of which 900,000 were unique. And now we have 6 million audio, of which more than 2.5 million are unique. So now we have more audio, more text, and again we swapped between. Now the data set is formatted in an instruction tuning set, in an instruction tuning way, where we randomly swap the generative and discriminative task, where we're like, this is the input, which is like the audio tokens in the first, and then you're like, describe the sound in the audio clip of the bell in the audio clips in detail, and the assistant goes like, the bell in the audio clip has bright, high-pitched ringing sound with high pitch and a short duration. The data set was structured this way, and then again, we gave it the next token prediction. There was also, when we swap it with the generative task, it just looked like, describe the sound of the bell in this audio clip in details, and it goes to the bell, and then you're like, can you generate it? And then this was how the data set was formatted. And we tried to do next token prediction. So the overall data set used were, for pre-training was the OpenQA closed caption only, but for fine-tuning with instruction prompt, it was the all OpenQA, which include open-ended and closed-ended questions. Wave caps we added, and we also added the FMA, but this was used for both pre-training and fine-tuning. Wave caps and FMA did not have like a prompt, but FMA had the yawner, so we sort of just compiled our own, like, oh, this song is of jazz, or this song is rock, etc., like this. Rule-based, it was not prompted through an LLM or something. And then we trained the model on 32 A100s for 1 day, 16 hours. It's still training. We still believe it's undertrained, but it shows very nice chitty-chatty natural language reasoning capabilities. However, it still lags in generation capabilities. Once in a while, I can get something funny out of it, which I will share. But some examples of its chitty chattiness is like, you would be like, I gave it like a piano, the prompt was dramatic piano. It tokenized like this, the tokenizing code. So that's how the audio language looks like. It goes like audio tokens. And then you ask it, wait, I'll just point the pointer. Which music instrument is heard in this audio clip? Describe in detail. How does the music instrument works? So I haven't told it anything about it's a piano or something. So it goes like, the music instrument heard in this audio clip is a piano. It produces sound by striking the strings inside with hammers and then amplifying the sound through the speaker system. So that was pretty cool to see some chitty chattiness in a language model with some reasoning of what I've given as an input. And this is pretty cool. The description task is fun to play with also. And that's what the audio was. It also sometimes wrongly classified this as a harp, but I feel like it still passes for that. But yeah, it was very adamant about piano and harp. I tried to say, is it a guitar? And it said, no, it's not a guitar, and stuff like this. So it knew what it was talking about, sort of. Some cherry-picked generation examples. Chicken noises, of course. And it goes on for 10 seconds. So it's because the audio, I think the data set was, at least the VAE representations were trained on a lot of music. It has the habit of generating things over and over and over and over again. Which also LLMs, when under trained, they try to repeat what they have generated already. And it goes on for 10 seconds. We have some saxophone-ish behavior. Siren again. Siren works for some reason. When I said that they give me an electronic drum loop, it just gave me one beat. When I said give me water dripping, it was, and it goes on for 10 seconds. So it really likes repeating things, which is a sign of an undertrained LLM, sort of early signs. But yeah, cool. There are some implementation nitty-gritties. Yes.
What is the frame rate of the audio tokens?
It's so
Per second.
no less. So like for 1 second, it's 21 tokens per second. Yeah. So yeah, 20-ish.
Interesting to compute the correlation of the beats you get and the token. Right.
Yeah. Perhaps yeah, that could be a good way we can think. But yeah, some other implementation nitty-gritties is like which. Generally, it's not available, but we try to do it because it's sometimes hidden in a lot of papers, so we wanted to put it out there. We also thought that the model can very easily cheat because it knows a lot of text, and when I trained it just text only, in a minute it started to adapt to text. So we also weighted the audio loss, so loss for audio token was 10 times more penalized than the loss for text. So we gave it a leeway to perhaps incorrectly predict the text, but still focus more on audio tokens, but then it still learned very nice how to generate text instead. There is this Z-loss that was introduced in Palm for training stabilization and avoiding exploding logits. We also use that. It's sort of like a regularization, keeps it prevents from the final output of the hidden layers logits to explode. Kind of useful, and they use it in Chameleon and other hacks as well. We also implemented this and used this. And we didn't face any training instabilities. Could be because of this. Some other results and conclusions. So we evaluated these LLMs with FENS and SPICE scores. So FENS and SPICE they try to correlate more on. It was a line from the LTU paper, at least for SPICE, they try to match the overlapping words and they ignore the synonyms. So these matrices, while they show some performance, still should be taken with a grain of salt. In all of these matrices, the higher is better. So LTU definitely being baseline because we use their data set. And had the discrete representation instead of more continuous and fine-grained ones. We could, at least in metric, compete in audio captioning performance, and this is how the metric evolved during training. As the model is training, it's starting to use more words and vocabulary, different vocabulary, and having a bit of a upward curve with a bit of shakiness once in a while. So the idea is that we're training the LLM further to see where it comes out to be. But for now, we can play. I have played around a lot with its chitty chattiness and audio description capabilities, which is quite fun to play with. So I think we'll end quite early. I will conclude it actually. So we investigated the use of low bitrate causal quantized audio representation to fine-tune the large language model with low-rank adapters for audio comprehension and generation task. And unlike previous method, we, instead of using continuous audio representation, we learned a discrete audio language, discrete language of audio sort of through causal variation quantization, and achieved an ultra-low bit rate of 0.29 kbps. These audio tokens then we used to try to fine-tune the Llama 7 billion model for multimodal task, treating audio as, again, language with a left-to-right inductive bias for training and qualitative analysis. With this, I would like to thank each and all of you for attending this talk, and also this work would not have been possible without Hennes, Nebosha, and the rest of the ARC team. Thank you for these fun 12 weeks, and I'm really grateful to be here with such brilliant people. Thank you very much. Time for questions.
So do you have any intuition as to what features are actually encoded by the VAE and the tokenization process?
So the intuition from the paper was released later when we started using it and everything. So the model, at least the base VAE, is trained on a lot of music data, and you could see with the repetition that there are some axes that once it's figured out, oh, it needs to repeat in a loop, and then it just goes on and on. So there's more music information, and somewhere in one of those codec is like repeat things, and then it goes like I've got it, and then it just goes boop, 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 on something like this. So that's a high level intuition of what we're seeing right now.
Questions?
Hi, Shivam. Thank you for your presentation. Can I ask?
Thank you for asking question, Mr. Jingwa.
Yeah, thank you. So I want to ask the LLM evaluation part. So I noticed that you used ESA50 for evaluation. Can I also, what you say in the fence and spice matrix on that, you mean you use the label name as the text directly, right?
No, yeah, exactly. So whatever came out, we put it directly as in fence and spice evaluation. But yeah, the correct evaluation for this would be having some more of an classification accuracy. So the idea is like we're exploring is like have clap or something to put it into some dimension and then do the top 1 or top 2, whatever classification type of ranking on this.
And the LTU you are mentioning here is LTU S or? I mean
No, the LTU, just the audio without the speech part.
Okay, got it. Thank you.
Thanks for a very nice presentation. My question is, so you said you played around a lot with the parameters or whatever to make it more chitty-chatty.
Yeah.
Is there like a loss function, an objective loss function you could use for that? Like,
no, essentially everything was in the dataset. The way we structured the dataset, now it has like these instruction prompts, like now the user is speaking this thing, now the assistant is speaking this thing. And then once you prompt, it's still an autocomplete type of thing. You say, user type something, and then at assistant you put a colon and you're like, now complete this. And then it becomes, because it was in the data set that it's a bit more chitty-chatty, it starts giving more chitty-chatty responses.
Oh, okay.
So it's still the next token prediction. That's the benefit of the LLMs, that you have this next token simple prediction, and then you can make it do fun things with it, with just autocomplete type of problem, as easy as autocomplete,
Okay. So the real loss function there is just, is it correctly predicting the next?
Exactly, given the context, given what it has generated everything before.
All right.
So I'm wondering, do you have any idea if it could be that next token prediction is not a good target for generating audio, which might be a reason why it generated only like repetitive things, because in audio you can pretty easy, there's a lot of redundancy over time, and it seems a rather easy task to predict what's in the next couple of 100 milliseconds coming, rather than maybe it would help to make a harder prediction task, maybe predict longer into the future at once or something like that. Do you think that could help? Instead of only one token at a time?
Yeah, I mean, there might be, but that's like the sort of other decoding tasks, like speculative decoding and like multi-head decoding that was introduced, I think this year only, at least multi-head decoding. But this is still a work in progress type of thing. But I think there have been a lot of works that, like quantization of audio works, is just semantic quantization is still an active research, I would say, that this is not the thing that's answered. Because if you think about it, it's in a very, one of the things that I think is that the entropy in the quantized token itself is too much. So the model really struggles to predict the next token correctly. It could be improved by, I feel, a bit better semantic tokenization, but it's just we didn't have anything available then. But I still feel like the next token prediction still should be at least better than what we got. I mean, it works for images, so it should also work for audio, I feel.
Have you tried to listen to those tokens? How they sound?
Yeah, those reconstructions that I saw, I shared.
Not just one token. What are the bricks of the audio?
Oh, Atom. No, actually. I always had at least 20 or something to have at least 1 second of audio. Otherwise, my decoder, I don't know how it will behave. But I did randomly chop them in and out, and you would get the exact chopped thing, variation out.
The tokens are assumed to be the same duration, right?
Yeah, while modeling, yes.
1/21st of the second.
Yes. Yeah.
Okay, thank you.
Hi, thanks for a great talk. So I'm wondering, have you tried to look into the distribution of the audio codebook? So my question is, do you think there's a specific set of codebook for, say, chicken speech and another set for, say, guitar? Or do you think the codebook are maybe intertwined for different categories?
That's something I didn't do. But while training, I did keep an eye on the perplexity and the codebook usage. Right. And in each batch, the codebook was used very uniformly. Oh. So that basically means that I feel it hard that one token essentially just takes the entire, like, I am the chicken noise kind of problem. As long as the codebook usage was uniformly distributed, I feel that was a good indication that the model is trying to explore all the space it has available. Yeah, but I didn't, that was one of the things that I wanted to, but I couldn't because of the time. When I was like, okay, I'll take this cat noise and put it and project it in some Disney plot or something. We did talk about this, but yeah, unfortunately I couldn't do it, yes.
I have a second question. So, so I would assume that the audio input are kind of smoothed over time. So, did you also observe some smoothness in the audio codebook, or is like every consecutive code different, like in the same?
No, clip? No, it was quite different. Okay. There was no pattern in the audio codebook that I could see from naked eye. Yeah.
Oh, okay. Thank you.
I do have some samples. The audio codebook, like these, except for the pretty formatting I did, except for that all these numbers were quite different from what it had, yeah.
There's a question in the chat.
Oh, I'm sorry, that's my fault. What was the question? Whoever had the question, do you want to just unmute and ask?
Yeah, hi, can you hear me?
Yes.
Yeah, thanks for a great talk. I was just wondering if you have an idea on how the model would behave if you were to use, let's say, musical notes instead of English language.
I think that will restrict it to like music generation and something. But I think those are nicer representation than natural language when we talk about music. So that'll probably be a nicer way, nicer data, easier problem to tackle than to dealing with natural language, I feel. But I could be wrong. I'm not an expert in musical representation, honestly.
Thanks.
Yeah.
Thanks.
Yeah.
Thanks.
Thanks for the question. Yes, I've been.
Thanks for the great talk. I want to say maybe two random suggestions.
Yes.
Recently, I triggered some paper. One paper is called AnyGPT. That model can take speech, text, and image as input and generate speech, text, audio, music, anything. And that paper, they have a really handcrafted data curation procedure. So with that data, the AnyGPT model can generate very good quality audio and speech. Maybe because I think in your project you don't do the data curation and data cleaning, and maybe this is a very promising direction. And another thing I think is that for the language modeling, usually the language model will handle the semantic information. For audio, it's audio event information. For speech, it's phonetic information. And for the tokenizer stable audio, I think it doesn't have such disentangled thing for semantic and detailed information. Maybe if you let the language model ease the problem, for example, it only take the next token prediction for the semantic tokens and let the decoder do some rendering to compensate for the detailed information, it will be better. Yeah, just some random suggestions.
Yeah, I agree. I mean, yeah, it's only 12 weeks, so there's only limited thing we could do. And data curation it takes time. It's the most extensive part of any work that I've done, and so I took an easier route to like, works for the LTU, should work for me. But it works for the LTU use case, which is the audio description task. But perhaps you're right that there's 100% a lot of inconsistencies in the data set that might hinder the generation performance. I also like the idea of having giving more work to decoder. But essentially what happens is like these language models, what I noticed is at least the smaller ones, they do face catastrophic. They have very memory of a goldfish they have. The moment I give it a different data, it just forgets everything it knows, and it's like, now I am honest to this data. And there is a lot of work that goes on into this catastrophic forgetting. So that's why I did the simplest thing that I could do is like here, next token prediction. Token ideally should have everything. But also, yeah, the VAE representations were more music-based, so I agree that the semantic information of audio might not be there.
Or at least since this question came up a few times now, but there's a bit of a divide between when you say semantic, do you mean semantic acoustically or semantic in terms of like English? So if I say like cat and dog in English are very different concepts semantically, but acoustically they're quite similar. They're animal sounds versus other sounds, right? So the VAE was not trained. The VAE was trained for reconstruction. So it just tries to reconstruct audio. And for that, it might have to learn acoustically semantic, meaningful relationships. But they don't necessarily translate well to like this kind of English or natural language semantics. And so then, which makes the generation task harder because the model has to actually piece together acoustic tokens rather than just say, find the cat token and then just generate from the cat token whatever cat sound that some diffusion model could generate. So it's a bit of a trade-off, I feel. Because maybe with this way, when you have acoustically, semantically encoded tokens, you also minimize, hopefully, the chances of hallucinating too much.
Yeah.
Because it has to come up with some acoustically meaningful thing, but not necessarily.
Yeah, one more thing if I would do, if you like, I will train a bit more. I will unfreeze some of the layers and train the Llama's layers as well. I think LoRA in itself is having a hard time trying to learn the language of audio. The same thing if you do with just text, it just quickly adapts to it because it knows text and it's like, new text tokens, but these new audio tokens were initialized from scratch. And yeah, so that's also different.
If not, let's thank the speaker again. Thank you, Shivam.
Thank you very much.